Log on, tune in, find out. Another good idea from Cambridge.
This is a very natural generalization of the simplest possible process, which is the sum of independent equidistributed random variable on Z, let's say, or R. And then people started to ask questions, well, are there central limit theorems? Of course, if we want to have central limit theorem, we should have something like a Gaussian variable. What are Gaussian variables? If you ask what are Gaussian variables, well, you might think, well, in the classical case, there are all kind of possible definition, potential definition of Gaussian variables. For instance, you can use algebraic properties of Gaussian variables, and that seems to make great sense to use that sort of definition in the abstract setup. So you can, and then you can ask a lot of what are the algebraic definition and properties that extend to this very general setup. But to tell the truth, all these questions are somewhat misguided. And they are misguided because instead of thinking of the setup and view it as the interesting part of the problem, it kind of take all the classical questions and put them in this abstract setup. So for instance, there is no central limit theorem for random walks on groups if you want to think in terms of general groups and general loops. And there just can't be anything like that. And so if you start to try to very hard to prove such a theorem, you'll have to restrict and restrict and restrict yourself in some very unnatural ways. In this case, there is a very simple reason why. That's because central limit theorem by definition use scaling. And there is no scaling in groups, except on a very small collection of interesting groups, but a very small collection. Now, at the end of the 50s, 1958, Harry Keston defended his thesis at Cornell, and he started from a question of Marquardt on product of matrices, random matrices on SU2, and developed that into his thesis, which talked about random walks on group from a very general point of view. And of course, he proved this very interesting theorem that give a criterion for amenability in terms of random walks. So to say it very quickly, a group is amenable if and only if any symmetric random walks will have the property, whose support generates the group, will have the property that the probability of return at time n to the origin decay exponentially with n. Now he also posed a question that I want to discuss for a minute because it's typical of this point of view of using classical theory to ask questions in this abstract setup. He said, well, what are the groups that carry recurrent random walks? And that became known as, well, the potential answer, which was that the only groups that carry recurrent random walks are extension on Z of the finite group Z and Z2, if we stay in the finitely generated context. That conjecture, which became known as Keston conjecture, also it's not quite possible to find any trace of it in the literature. That question was taken very seriously and produced a lot of good work. But if you think about it, it's really a crazy question. You know, from the point of view of random walks on groups and from the point of view of groups, it's obvious from the conjecture that it's not an interesting question. You know, the only groups that are recurrent are trivial, and it's a very small, extremely small little corner Why would we be interested in characterizing this very small little corner? Now, it is true that technically, the fact that one was not able to prove the conjecture was interesting, but the question itself is not that interesting. I talk and I explain briefly why central limit theorems are not a good question in that context. Well, something that is a good question is the local central limit theorem, which is to try to say what the law of the random walk at time n, how does it behave depending on n and x. There is no rescaling in local central limit theorem, whereas in central limit theorem in the usual setup there is rescaling, so that's a big difference. But technically, local central limit theorem are a little bit harder than central limit theorem. And if we think about it, they are always proved, or almost always proved, by Fourier analysis, by taking the Fourier transform, characteristic function, and studying these objects. And the problem again is that on groups there is just no hope on general groups to use such techniques. Actually, in the 60s and 70s, people thought that representation theory would develop so well that maybe it would answer this question. Now, this is a completely stupid idea. It's not going to work. But I want to start by telling you about one beautiful theorem in that direction, and that's Philippe Bourgeois' theorem about random walk on semi-simple groups. So, for a minute, and that's not going to be the case most of the talk, but we are going to talk about Lie groups or continuous connected groups. So now Bourgeois theorems tell you that tell you more, but let's put it this way. So we have phi, which is a compactly supported continuous, let's say symmetric, I'm not sure that's necessary, probability density on G, and G is a semi-simple Lie group. So, for instance, if you don't know about semi-simple Lie groups so much, well, first of all, you should learn about them, but example would be SLNR, so the group of matrices with real coefficient and determinant 1. So, for such object, Bourgeois proved that I'm not trying to write it in the greatest generality, I'm just writing the simplest essence, that there is an asymptotic for the convolution of any such probability density, and it's of the form this is actually a half integer, so maybe I'll write it like that. Well, so this is a continuous density. It's positive at the origin, so it's positive on the neighborhood of the origins. That means it's positive on compact generating set in that group, because this is a connected group, and any generating any neighborhood of the origin is generating. And this gives an asymptotic to the probability of return, or to the density of the probability of return at the origin. It tells you that there is an integer a of G, which depends on the group in somewhat complicated way. It depends on the dimension and the root system, such that this quantity is equivalent to a constant time n to the minus ag over 2 time rho of n, and rho is the spectral radius of this thing. It's the L2 norm of phi as a convolution operator from on Z.
So this rho is strictly less than 1.
Well, I said semi-simple Lie group.
You're a bit compact.
So in this term, there are compact groups. I did it on purpose just to remind you that actually for Lie groups, there is a classification of amenability and non-amenability. And in particular, for semi-simple groups, the only non-amenable, the only amenable semi-simple groups are the compact ones. So either the group is compact, in which case this rho is 1, this A is 0, this goes to a constant, or it's non-compact, in which case it's non-amenable, rho is less than 1, and again this A is then given by a function as a known function of the dimension and now this.
Sorry, what is phi superscript minus at the A time period?
Well, this is just a function, a constant that depends on the choice of phi. Sorry, a function, a constant. This is just a constant. Okay.
No, the question was about phi to the n.
Oh, this is a convolution of phi by itself n times. Thank you. Sorry. Okay. So this is proved by Fourier analysis. Depends on Harishandra's theory of the representation of these groups. It's a beautiful result, and it's one of very rare results of this type for non-abelian groups. I guess one obvious other example of such result would be for free groups. Actually, for some A2 tilde buildings, there are groups when one can get such result, but it's extremely limited. There is essentially no such result in general. And this brings me to the first open question I wanted to mention, and I find it one of the most striking from the theory of random walk of a group. So let me write it like that. What about random walk on SLNZ? So for instance, on SLNZ, there are many natural sets of generators, but for instance, take the identity plus elementary matrices. To put a 1 somewhere, you know, that's a nice set of generators. Take the uniform measure on that set, throw in the identity if you want to make sure there is no periodicity problem or any kind. Then the question is, so we know that this is a non-amenable group, so we know that phi n, the convolution power of any natural distributions, will correspond to a rho less than 1, and so there is exponential decay. But that's about what's the extent of our understanding. We don't know any local theorem of that sort.
Bourgeois theorem cannot help.
Bourgeois, nobody has been able to use Bourgeois theorem or the proof, or it's very important here that the measure of the phi is a density, not a discrete measure. It's not known that there is a lower bound with a polynomial, things like that. And that's kind of discouraging. After all, SLNZ is your most popular, should be your most popular non-commutative big groups. You know, this is the first one one would think about it. One would think about it.
What is the K of G if this is SLN phi? If G is SLN?
Well, I don't want to say it's a sum of positive roots over 2 plus a dimension or something like that.
It is some depends on some on M. Well, on M. SL, if it is for example,
A of G depends only on the group G, not on phi.
for example, SL3, it is equal to
On itself free, it's free, but if I remember correctly, I'm not even completely sure, but I think so. No, no, it's already more than free. Sorry, for SL3, for SL2 it's free. But it's a known number, I just didn't check what it is again. Okay.
Your question is also open for n equal to?
No, actually for n equal 2, so SL2 R is almost a free group. And so one can do things. But I don't think very much is it's actually hard to do them. So not so many people have tried to do them. People kind of know they can do it by using the free group case. But certainly it would be very hard to do an arbitrary measure on SL2R. The only things that have been done are for very particular choice of distribution on SL2R. For instance, the one that would come with the generator that makes the graph of SL2R very simple and close to a group. Okay.
take a co-compact lattice instead of SL.
No. Yeah, so SL2R, the question is, what about co-compact lattices? SL and Z is not co-compact, it's a finite volume, it's not co-compact. So co-compact should be much closer to the other one, but nothing. Nothing. I'll come back to that question. Okay. So at the end of the 70s, the French school in particular, Guivart and other people during the 60s and 70s worked very hard on this question. Bourgeois is part of this school, especially at this time. This was his thesis. But they proved many interesting things. For instance, they solved Keston's problem for linear groups. But they couldn't touch any result regarding general groups. There is a huge difference, and you might know or not know, most mathematicians don't understand that actually, between linear groups and other groups, general groups. And so on linear groups, one can use structure theories that tell you about the group, and you can do something. In general, it's a very different question. Okay, so in the 80s, things changed for various reasons. So I would like to cite a very famous and beautiful article by Kajmanovic and Vershik in Annals of Probability, who talked about random walks in really important and new ways if you compare to what comes before. There is a work of Gromov who convinced many of us that studying a discrete group as metric space was a very important and interesting subject. I remember actually I was in Cambridge when my advisor Nick Varopoulos told me, well, I'm working on random walks on groups, but you shouldn't do that because you will never get a job if you do that. That was just at the early 1980s, and it was not considered very fashionable at the time to do something discrete like that. But Michael Gromov certainly changed that clearly. And of course, my advisor Varopoulos worked on these problems, and I'll talk about some of his results. So from all this came a very different point of view from the previous one, which was kind of transporting classical question to this. Here the question, which really comes from Gromov, is okay, these groups are, and for a while I'm going to focus mostly on finitely generated groups. So I'm thinking about finitely generated groups and their Cayley graphs. So I have a geometric structure. This is extremely interesting. We should try to understand those things, classify them, understand their property, and it touches upon many, many things. Of course, they are very complex objects, and to try to understand them better, one can try to embed them in Banach spaces or things like that, right? That's, but at the time we didn't think about that so much. So the question is, for me here, is to understand random walks from these viewpoints, which is to try to see how random walks, the properties of random walks, connect to the property, the algebraic geometric property of the group. And this is a completely different point of view than asking whether there are central limit theorems. So let's see, starting from 1980 on, the focus moves to relation to geometry slash algebra, and also associated to this is all groups. So there is something interesting about all groups. I'm not sure Gromov said that, but people say that Gromov said that any inequality or any statement about all groups is necessarily trivial.
If it's true.
If it's true. There are counterexamples to, but I'm sure Gromov had a precise idea behind it, and to some extent it's true, of course. The point again is that general groups are incredibly, we have no idea what they are. That's something, again, that most of us still don't understand completely or forget all the time. For instance, I've spent most of my career thinking about groups, and I still have the impression I understand groups, where I have to remind myself that, no, we don't. So anyway, but still, the point here is that asking the question with the idea that you want to understand all groups, almost all groups, very large collections of groups, instead of small examples, is very important. That's the point of this. And so from this point of view, what do we want to do? So let's say instead of all groups, it's really a lot of them. And it's actually a problem in logic, right? What this means, even for abelian groups. So I'm thinking, in fact, of all finitely generated groups. So on the finitely generated groups, I want to think about distribution, probability distribution phi. And I really want this phi to be a small phi. And I want to look at the probability of return of the random walk. I'm going to take it that most of the time, and sometimes I'll forget, but at even times, sorry. And I am always assuming that phi is symmetric. By that I mean that it gives the same probability to x and its inverse. And this property has the great advantage of making this quantity decreasing. So that's the reason. That's very nice. We have a decreasing function of time. And that's what we want to try to understand from the random walk point of view. And we want to try to understand it in the way I explained, that is, for most groups, for all groups, and try to understand how it relates to the fundamental structure of the group in question. So, for instance, the simplest question which was in the air from the beginning was, if the group is very large, does it mean that this quantity decay very fast? If the group is very large and you work on it, then you should have only a very small probability to return to your starting point. Now, of course, this was a question from the beginning, because for Keston's conjecture, this is essentially the essence of it. the essence of it is that if the most groups are large, and so most groups should be transient because this quantity will decay very fast to zero. Now, this is so. I take the point of view that this is a fundamental question about random walks on groups. I will talk about some other questions that are very interesting, I hope. But if there is one question only, this I think should be. But now let's talk about geometry and a very famous question. One can think of this Cayley graph, the Cayley graph of a group like this. So now I am fixing a generating set. It's a finite symmetric generating set. I have the Cayley graph corresponding to this set and the corresponding left invariant distance, which is obtained as a world distance. Now, isoperimetry consists in comparing the size of a finite set A and the size of its boundary. This will denote the boundary. The boundary are, let's say, well, I don't know, the point in A which have a neighbor in A complement. Now, there are several ways to do that, and I'm going to choose one. That's the one I like most personally, but it may be not the most classical one. So let me define this function. I hope I got it right. I always get it. So for any set A, I compute the ratio between the size of A and the size of the boundary. That's maybe a big number, or it's bigger than 1 after all, because I took boundary of A to be a subset of A. I make it an increasing function of n by taking this supremum over all small sets. So this is an increasing function of n. And of course, you can think about it in the following way. If I'm right. This function J describe some sort of isoperimetric inequality in this form. Right? It's the optimal thing that you can put there. It controls the size of A in this strange form with the volume of A. It's more or less equivalent to other definitions, but I want to use this one. So what's interesting about this function? Well, first of all, of course, the boundary of A depends on the choice of generators, but in fact, it does not really different choices of generators give equivalent and so you can define equivalent mean the following. And I'm going to use, this notion of equivalent all the time. So I conjugate by constant. And so if you use this as an equivalent class on functions, especially on increasing function, it's a very nice equivalent class. Otherwise, you should be very careful what it means. But on increasing function, on monotone function like that, it's a very nice equivalent class. And we can define a geometric invariant, which is a group invariant, which is a class of this function on G. Usually I will not be pedantic and pick any one of them and use that as my functional. So let's look at some example. Well, on ZD, well, there is a classical isoperimetric inequality which tells us what this function G is, and it will take you a minute to, if you act like me, to see what it is, but it's this. On non-amenable groups, by definition, or by Follner criteria, this is a constant. And then on any other groups, well, it's a finding exercise to try to find out about this function. So one question is whether there are connection between this question, the geometric question, and the random walk question. And there are plenty, but I'm not going to review them immediately. One question that comes up immediately when you see that is the following. Okay, for any generating set like we used for defining J, we get also a probability distribution, which is speaking uniformly at random in that generating set. So we get different phi's, and the question is whether or not this, like J, is a group invariant. Because if it's not, then that's bad luck for us, because we want to think about random walk in terms of the group structure. And in some sense, if this really depends on the set of generators, then maybe the question is not so good. On the other hand, the fact that this does not depend on the set of generators is a very simple result. It's a simple observation. The question of whether this depends or not on the set of generators is not simple. So it's a theorem that it does. This is a term of Christophe Pittet and myself. So there exists a group invariant, which is a function or a class of function according to this definition, such that for any admissible phi, I'll tell you in a minute what admissible means. These tell you that there are many, many different random walks. They all have the same behavior. All these random walks are the one that I call admissible. So I'm talking only about symmetric random walks, first of all. And then to be admissible, well, the simplest definition would be finitely supported with generating support. So in particular, any uniform measure on the generating set is admissible, a symmetric generating set, and so indeed we get the similar result that all the random walks behave the same. Okay? In fact, and I'll come back to that if I have time, the class of admissible phi is much larger than that in that it contains all phi that have second moment on the group. So, you know, on the group we have a norm, which is this distance, the world norm. And so as long as phi integrate the square of the distance function, then this is correct.
But in general, it's not correct. So if you take arbitrary phi.
Oh, of course, it's complete. I'll come back to that, actually. That's one of the questions I want to mention.
Is it the sharp condition? Is the L2 condition the sharp condition?
Sorry?
Is L2 the sharp?
Well, not very far from being sharp. Depends how you define sharp.
Very sharp.
Okay? Okay, so now we have three invariants that I think I mentioned. One I didn't mention, but it's the simplest, so I can mention it like that. Volume growth, right? How many points are there in the ball of radius n for our set of generators? So change the generator set, that doesn't change the behavior of the volume growth from the point of view is this equivalence that I'm always using. The isoperimetric function, this one or your preferred one, another one if you want. The random walk return to the origin, the probability of return to the origin. Those are invariant of the group. All of them are actually invariant of quasi-isometries, which is a much stronger and much more interesting result than just invariant of the group. Again, it's essentially simple or trivial for the first two, for the volume growth and for the isoperimetric function. It's rather non-trivial, but it's kind of part of this theorem for the probability of return. Now, I want to insist, for those who haven't seen those things before or haven't never worked on them, that there are many, many groups for which we don't know how to compute V, the volume growth, where we have no idea what the isoperimetric function is, and where we have no idea what the probability of return. In fact, that's the case for, well, I don't know, I don't want to say most group because then it depends on what you mean by most. But there are many, many classes, many examples, many interesting examples where we don't know. There are groups for which we are not able to decide whether they are amenable or non-amenable. There are groups for which we have no idea what exact compartment of volume growth is. And if we don't know the volume growth, then probably we don't know very much about the other questions. On the other hand, and that brings me back to what I said at the beginning regarding Lie groups and linear groups. For linear groups or some sort, there is a very nice picture. That will be the only very serious term I am going to write down, actually. So I call it structure theorem. So it's for linear groups. Actually, it's as you'll see. So assume that G is discrete. G is still finitely generated. Okay, that will make my life simpler. G is a discrete subgroup of a connected group. So discrete means that the topology that this finitely generated group inherits from the group in which it lives is a discrete topology. So that's a condition on this linear group. So assume this, and there is only three possible behaviors for all these invariants that we have. So maybe it's non-amenable. This is of course equivalent to J is 1, that's Follner's criteria for non-amenability. It's equivalent to phi J to be an exponential. This is Keston's criteria. It's not equivalent, of course, but of course the volume is exponential. just a remark about the third invariant. One can say more, of course. I see that I can't refrain to say that, of course, these groups contains a free group, a non-trivial free group. That's Stitt's theorem. So, amenable and exponential volume growth, that's equivalent to J n is log n, and it's equivalent to phi of G is exponential minus minus n to the power 1/3. And then amenable and not of exponential growth. I can say that like that, actually. But then I don't have too much space. Then, in fact, these groups are of polynomial growth. There is an integer d that describes their volume growth. That's Gromov's theorem. And then, in this case, the function j is n 1 over d in a way that's similar to the classical case of ZD. And similarly, the random walk behavior is given by minus d over 2. Sorry for writing. So this is the simplest case, the nicest case, a case that's like a classical case. In fact, the group in that case are all virtually nilpotent, so essentially it's a nilpotent case. All the groups in category 2 and 3 are polycyclic groups, so in fact they have a rather simple structure. This is why there is such a huge difference between linear groups and general groups.
Why do you need discreteness in this result?
Because you want example. Okay, so let me give you an example. So the question was, why do we need to have a embedding so that the group is discrete? Okay, so let me give an example that will be interesting. One of the simplest case is a case where the ambient group is the affine group of the line. This is a Lie group, of course, the Lie group of all transformation AX plus B. This is actually a good example because, how do we know groups? Well, I like to say it the following way. There is a there are many ways we can know groups. But one of them that's interesting and pretty capture a lot is the idea of we have really a black box that tells us how to multiply things, and we have generators. Now, this black box sometimes is given to us in a way that we think we understand the black box, but in fact we don't. For instance, in this case, the black box is something we all understand pretty well. It's composition of affine transformation. That's not so hard, right? So here there are several groups we can consider. For instance, the group generated by these two transformations and their inverse. Right? So this is also called the Baum-Flag-Solitor group because of its presentation. it's a finitely generated group by definition. It's embedded, or it's a subgroup of the affine group of the line, of the little connected group. It's not discrete, right? Because they are, you know, 2 to the minus n transformation with very small components that are very far away from the identity in this group. Now, for this group, we know everything. The volume is exponential. Please find a free semigroup. This guy is actually log n again, and phi of g of n is exponential minus n 1/3. Okay? So that's an example that shows that it's not necessary to be a discrete group in a Lie group to have this behavior. Also, maybe this guy can be put into another Lie group as a discrete group. That depends on your definition of Lie group, maybe. But here's another example. So this is first example. Now we can look at the group which is generated by the translation x1 and some different lambda. Now, it's not hard, it's a very nice exercise to see that what is important here is whether, well, one thing that's important is whether lambda is algebraic or not, and its degree of algebraicity. If lambda is algebraic, then the result will be similar to the case of the integer 2, which is algebraic. If lambda is transcendent, then this group is actually better understood as a produit en couronne, risk product. I forgot it's like that. Nobody knows this sign anywhere. So this means risk product, and I'll tell you what it is if you don't know.
/WR.
Maybe it's the other way. Or
It's an integral.
No, this is integral.
yeah, so it's the other way. I'm dyslexic, so it's very hard for me. So this is actually this group. And this group is, what does it mean? This is Z acting by translation of the indices on the sum of infinitely many copies of Z. Or if you prefer, it's the straight Z with very fancy lamps that takes infinitely many colors or infinitely many shades. And where, this doesn't describe to you the group action, but the group action is not very complicated. So let me write it like that. Z semi-direct product is the sum of copies of Z, so I call it Zi. So the action is just translation on the indices. You add coordinates, but there is an action of the other component of Z that translates. And for this group, I'm going to write it here. So the volume is exponential. Oh, okay. I don't want to write Gn because I haven't checked. I'll give you phi. We know exactly what it is, but so this is a counterexample.
So you need this kit.
The simplest counterexample. Okay. So, having described all that, let me ask some open questions. Oh, first of all, I should tell you a little bit about this beautiful theorem. So first of all, I call it the structure theorem because, you know, it describes exactly, it classifies everything in that case. But also, it depends very much on structure theorem about linear groups. So it essentially depends. I don't want, you know, you might try to make it depends about as little as possible. Of course, that would be sensible. But okay, let me, you know, you might use Tit's alternative to separate the first case for the otherwise. Then you use the fact that if you are not non-amenable, you are essentially polycyclic, which is a beautiful algebraic result from Malchev and many other people, Mosto and others have worked on this. The last point does not actually depend on Gromov's theorem, also it looks like it does. That's because of what I just said. We know that it's virtually polycyclic. So for polycyclic group, one doesn't need Gromov's theorem to get that either they have exponential volume growth or they have polynomial volume growth, and they are virtually nilpotent, but still it's the work of Guivarch, for instance, and Wolf and Milner. So that's about the different classes of groups that appear in this theorem. The results, well, the first line, the non-amenable case, is the work of Follner and Kesten. And the rest is essentially the work of Varopoulos. Also, some pieces of it are due to other people. The lower bound for this function is due to another student of Varopoulos, George Alexopoulos in Orsay. The estimate of this function is actually due to Thierry Coulon and myself and Christophe Pittet, again, for the upper bound. Okay.
Is the n to the 1/3 something that is related to something that we know about? Where does it come from? It looks odd without it.
No. Also, you know, in some cases, you can try to make it look like something you know. But I would say no. The n to the 1/3 is implied by this function. So there are some relation between these different results. Okay. So what are interesting questions in this case? Well, there are many interesting questions. For instance, the solvable groups. Well, in solvable groups, there are many possible behaviors. So one question I find very interesting and intriguing characterize all groups with another way to ask this question is characterize all group with isoperimetry of type log n. Like, it's not, we don't know that characterizing one is equivalent to characterizing the other. Also, it's probably maybe true. So since I have written summaries product, I can now use, now in my notation, this Z is this Z. Okay? And this Z is this Z. I'm not sure it's my usual notation, but it's my notation right now. So, which one do I want? Okay. That's the one that's easy to understand. The lengths are either on or off. This is a group with 2 elements. So this big packet over there is a sum of infinitely many copies of the group at 2 elements. Sum means there is only finitely many non-trivial coordinates. And now there are 1 length for each element in ZD on the lattice, and the lattice, these groups are indexed by this. And again, the action is by translation on the indices. So for this group, this is to tell you about solvable group. This is a solvable group. It's a very simple solvable group, right? Made of essentially 2 abelian groups. The infinite product here and this guy. So I believe, again, I didn't check this one actually, but I think this is correct. Don't use it to prove something very important without checking. I'm not sure, but I think that's the correct function. I'm sure about phi j. You want to ask your question again, please? So the question was, the question is, you know, is this thing coming from something we know? In this case, it does. So for this particular example, which is a very different question, actually, but this estimate, this result is essentially equivalent to a well-known result of Donsker and Vardan that give you.
It's not 1.
Sorry.
Is not 1.
This one is okay. 1/3.
But there was a log into the 2/3.
No, there was Z here.
Oh, sorry. Okay.
This is equivalent to a classical result of Donsker and Vardan that give you the Laplace transform of the number of visited points. The asymptotic behavior of the Laplace transform of the number of visited points by simple random walk on ZD. You see, each time a group is explicitly given to you in function of very nice other groups, then you can probably write down you can do stochastic calculus and write down the other coordinates in terms of more fundamental coordinates. So that's what happened here. And then the question you are asking is a question about maybe some classical functional, if you are lucky, or some non-classical functional, if you are even more lucky, and then you get some job to do, of simple random walk. This, unfortunately, doesn't carry you very far, because most groups are not of that type. But it certainly gives you an opportunity to obtain interesting results. For instance, this example is already in the paper of Kajmanovic and Vershik with an interesting result, also not as precise as this. And it's, it can come to some surprise that you have amenable groups that have behaviors that come very, very close to the non-amenable behavior, the exponential behavior. You can do better than that with other groups. So I'll finish, and I had many more things to say, but I'll finish with one fundamental problem that I believe is very hard, unfortunately. And it's the question of whether the two main invariants that I have discussed today are equivalent invariants of a group. That is, if a group has the same isoperimetric function, does it mean that they have the same random walk behavior? Or conversely, if they have the same random walk behavior, do they have the same isoperimetric function? That would be a terrific result. Not so much because it will let you do more. I think in all the example we have, if we can do one, we can probably do the other. That's probably not completely true. The Basilica group, for those who know, would be an example of group where we know more about groundwork than we know about isotelemetry. I think it's fair to say. But the question, the most interesting question is, if we want to prove that in full generative, assuming it's true, maybe I'm foolish to think that maybe it's true, it requires some understanding of why would it be true. It has to be true because we are talking about K-graphs of groups. But when you talk about general K-graphs of groups, it's very hard to prove anything, to capture the essential properties that are different from, let's say, other graphs. In this theorem, there is a result that says that if you have a certain volume growth, indeed, the return of probability decay fast, in some sense. And that's one interesting result that's valid for all groups. And this was a very difficult result to obtain. Also, the proof is very simple. The proof cannot be very complicated because if it's a true proof for all groups, what can you do? But you have to find exactly how to capture the group structure to get what you want. So I'm not very optimistic about proving the equivalence between J and G. I'm not even sure, there are many groups we don't have any idea what they are, so whether it's true or not, I don't know. Okay, I'll stop here.